Hi everyone, so today we're going to be talking about timers. And to talk about timers, we need to talk about how the PIC32 deals with clocks. And so if you take a look at the board right here, you'll see that there's the main chip right there, and then there is the main crystal that drives the processor right there. And so it's important to point out that without a clock, the computer really can't work. And so we need to have a discussion about clocks. And then beyond that, without timers, the microprocessor really can't do much useful work in interaction with the world, because it needs to be able to time different events to measure time. And so that's why we have to talk about both the clocking system as well as the timing system on the processor. So when we're talking about the timing that's going on the PIC or any other microprocessor for that matter, we're talking about generally a relatively complicated set of components or subcomponents that sort of come together in order to make timing actually work properly. So we start with the crystal, and the crystal is found sort of right here, and it's what I'm calling right here the outside world. It's what you see on the outside of the processor itself. Over at this end of the data sheet that talks about the oscillator, we have the CPU core, and that's sort of inside of that little black chip. What we're trying to do is connect this outside world right here, where we have this crystal, to what's going on the inside. What's going on the inside, where the timer is, where the analog to digital converter is, where all of the useful things that we want our computer to do are found. Now, we have this crystal, this little black, or this little sort of metallic box or can, okay, and sometimes it's labeled, it should be labeled, saying something like it's got 8 megahertz or something coming out of it. And this is going to be connected in, this is referred to as the primary oscillator. And this primary oscillator has a path that comes in where we can select different modes for the primary oscillator, and it's controlled by what's referred to as the clock control logic. And this basically allows this multiplexer, you can see right here, this funny shape right here, to select where the main signal is coming from that drives the timing or the clocking on our CPU core. Now, we can use the crystal right here. We could use a low power resistor capacitor oscillator. We could use a secondary oscillator as well. There's these secondary oscillators, and sometimes you'll see these secondary oscillators with a sort of a weird crystal value, like 32.768 kilohertz. And the reason for these are low frequency crystals that have been specially tuned in order to be able to, once you get through all of the math that's in here, be able to get to, for instance, exactly 1 millisecond or 1 second or 60 seconds, 1 minute of actual real timing. These are useful for any timing related task or any clocking related task that basically syncs up with sort of human regular time. Whereas when we use these 8 megahertz, 4 megahertz, 16 megahertz crystals, that doesn't really come into account, because we can't hit exactly 1 second or 1 millisecond. So we have all of these, but in order to make all of this work, we generally need to either slow down or speed up the signal that's coming out of these clocks. So if we have an 8 megahertz crystal, we want to say speed it up to 80 megahertz internally on our system, the system clock. So we use something called a phased locked loop. And what this does is it takes the signal of the crystal and brings it up into this circuit up here, where you'll find some dividers and some multipliers. And this will allow us to change the 8 megahertz that's found on the outside of the chip into, say, at the peripheral bus clock, which drives the analog to digital converter or our timers, etc., we'll be able to bring this up to 40 megahertz or 20 megahertz or 80, one of these other values. So we need to figure out what the flow is of the original clock into the rest of the system. And so we have to figure out how to turn on particular registers, okay, in order to make this work. So that's what this session's about. Okay, so let's start with our primary oscillator. So looking at the Wikidot site for microchip right here, what you'll see is a description of the external clock or the external crystal mode. So if you have sort of a square wave input, you can use external clock. If you're using one of these crystals, which is typically how we do it, then you'll have this sort of sinusoidal wave come in through the crystal. The crystal is this little can that might say 8 megahertz on it, or a little box. So it might look like something like this, little silver can, or a little box like that that's on the board. So this crystal right here feeds into, there's the primary, the crystal right there, and it feeds into your system phase locked loop. You can also tap off of this in order to drive the USB. And in a lot of microcontrollers, the USB signaling has its own timing path. They want to get an exact frequency on the clocking signal for the USB in order to make it work. So that's generally handled separately from the main pathway for the clocking of the board. Anyway, so you've got your phase lock loop. The phase lock loop is broken up into 3 components: the input divider, then a multiplier, then an output divider. And the input divider will bring the external clocking signal to a specific band of frequencies that, for one reason or another, and we won't get into the details here, that the phase lock loop has to have a specific frequency in order for it to remain stable, in order for it to work. And I believe with the PIC32 MX, it's the input divider has to get the value of that to between 4 and 5 megahertz before it hits the multiplier. So we have a register that controls the input divider value to get it down to 4 to 5 megahertz. Then we have the multiplier, which will bring it up to a particular value. And then we'll have an output divider that will, in the end, either keep it at the value that was coming out of the multiplier or bring it down a little bit. So we get to choose some value based on a combination of these 3 things that comes out here. So we can go from an 8 megahertz over here to, say, for a maximum of 40 or 80 megahertz at this end. All right. And then we can have the system clock going at a particular value, say 80 megahertz. And then if we need the peripheral bus that's driving the analog to digital conversion, the timers, etc., or the counters, we can bring it down to, say, 40 megahertz or 20 megahertz or 1 megahertz. So it can be slower than the system clock. So you can do calculations like math at a high rate, and you can deal with your peripherals at a lower rate. All right. Now, from a practical perspective, we need to be able to actually set this up. And so it's important to know that in this sort of chain that we've got right here, where we go from the crystal all the way to the system clock, we have registers that we need to deal with. Now, there are 2 times at which the registers can be dealt with. The first is during boot up, and the other one is during runtime. And during boot up, we want to set up the crystal or the clocking pathway to be done in a way that the system will actually work in order to start running the program that's on board. So we set it up using these pragma statements that effectively set things up ahead of time before the program starts. It does it in a pre-compiling sort of phase of compiling your code. The keywords, I guess, that are being used for it are for instance these right here. We'll talk about these in a minute. They also have constants that are being used to set whether it's a multiplier by 20, a divide by 2, a divide by 1, these values are all defined in a header file. That header file has a particular chip number because every chip is going to be different. We generally with MPLAB-X don't have to worry so much about what that actual header file is named because we call xc.h to go and find it. And there's some scripting that goes on inside of xc.h that will go and find the specific numbered header file to be able to figure out these definitions. Okay, but if you need to go and take a look, you can actually go and find that that file, and it will show you which multiplier or divider values are permitted. In the actual source code, you will end up writing out things like your pragma statements, etc., at the top of the file, the C file that you're making. Now, going into the data sheet is always super important because that's where everything that is important about your chip lies, and every data sheet will be different. So it's important that when you're trying to figure out what's going on with the phase lock loop, that you go into the data sheet and read it. And so here is an excerpt from the clock generator for the PLL section of the data sheet. And so you'll see that there's some instructions about configuring the phase lock loop, and that it's important, for instance, to calculate that the input divider values are a particular thing and the output dividers are a particular thing. And it says here that set the PLL input divider and the initial PLL multiplier values in the dev CFG2 register when programming the part. And then at runtime, the PLL multiplier and PLL output divider can be changed to suit the application. So this is being set during the pragma section of the code. Whereas you can actually go in and change a different set of registers afterwards that will allow the output divider and the multiplier to change. And that's important because sometimes you need a really dynamic response of your clocking system. So when you're dealing with the boot up phase, you're dealing with the dev CFG registers. When you're dealing at runtime, so when the chip is executing, you're using the OSCON registers for doing effectively the same thing. So the OSCON registers, or oscillator control register, is a 32-bit register, bit 0 to bit 31 right there, and it has, unlike some simpler 8-bit processors, it has a lot of different settings that you can see all in here. And you can see, for instance, that the PLL output divider is defined right here. It's 3 bits. It's bits 29, 28, and 27. You also have the PLL multiplier, which is bit 18, 17, and 16. You can see that it's got 3 bits associated with it there, and this one has 3 bits associated with it there. We're talking, in this case in the chain, about the multiplier and the output divider. You'll notice that the input divider isn't found in here. You can't change the input divider during runtime, okay, or you shouldn't. All right, so when you go into the data sheet, you'll also see that the allowable ways that you can set up your multiplier and your divider are actually set out in the data sheet. So for instance, if you needed to know what the output divider values were that were permitted, you go into the data sheet and we'll say bits 29 to 27 are allowed to have values 111 all the way through 000. If you have 000 in the let me see, the PLL output div, so these bits right here, if they're set to 0, then you have a divide by 1 case, and so basically the value wouldn't change from the output of the multiplier. You would have 80 megahertz there, you would have 80 megahertz going out. But if you needed to reduce it, you could reduce it by a maximum of 256. So you could divide 80 megahertz by 256, and that would be the output here. Okay. So we also have the PB divider, which allows the peripheral bus clock divisor to be set. So if your system clock is running at 80 megahertz, you could choose the 2 bits for the PB divider right there to be divided by 4. So if I have an 80 megahertz system clock, I could divide by 4 right here to get a 20 megahertz peripheral bus clock. And why would that be important? Well, there's a number of reasons for it. One of them is power. The slower that you go, the less power is required to drive those peripherals, which can be important on a battery-powered application. But also, when you're doing certain communication processes, like using a serial port, sometimes you need to get the frequency of your serial port to a very specific value, and you only have a limited number of things that you can do in order to make that happen. And one of them is to reduce or change the peripheral bus clock to get it to a particular value that allows other registers to then multiply or divide in to get the communication frequency that you want for your timer. Okay, so you've got your peripheral bus clock, you have your PLL multiplier. The PLL multiplier in OSCON, where is it? Where is it? There it is, right there. They're hard to find. There's the PLL multiplier right there. And it can be chosen between values of 24, 21, 20, 19, 18, 17, 16, 15. So you can see that 0, 0 here might divide by 1, but 0, 0, 0 here doesn't multiply by 1. It's a multiplication of 15 all the way through 24. So it's important to go through the data sheet to figure out what those allowable divider and multiplier values are. Okay, now the input divider value isn't found in the OSCON register, the OSC CON or oscillator configuration register. It's only changeable during boot up, not during runtime. And so in order to modify it, you have to modify using the pragma statements one of 4 registers: dev CFG3, dev CFG2, dev CFG1, and dev CFG0. So device configuration registers 0, 1, 2, and 3. So dev CFG2 is right here. And where is idiv? Idiv, let me see, it's not that. It's not, there it is, right here. It's the bottom 3 bits of the dev CFG2 register. Let's see, can we see it in here as well? Dev CFG2, there it is, idiv right there. Okay, so in the data sheet you'll find it, and it's important that you go down, dig inside of the data sheet, and eventually you'll find it in there. Okay. So to summarize a little bit of what's going on in our crystal to system clock chain, we solder on our crystal, the little box, the little can. It feeds in its value. It can't be changed. It goes into our chip. It gets routed into our PLL. In our PLL, we can change the input divider, this right here. We can change the multiplier, this right here, and we can change the output divider, that right there, in order to get the system clock and also the peripheral bus clock that we want. The input divider has 1, 2, 3, 4, 5, 6, 7, 8. 8 possible values, divide by 1 all the way to divide by 12. The multiplier has, again, 8 values that allow multipliers of 15 through 24. And our output divider has 8 possible values, 0 through 111, and that allows dividing by 1 all the way to 256. Okay, so those are the possibilities, and any of those sort of combinations are possible in order to get your system clock out from an initial crystal. So you can see how this might be important to get the combinations right in order to get the behavior on your board, on your chip, to be what you expect. All right, now let's take a look at the other dev CFGs. Okay, so you've got dev CFG1. You'll find that in dev CFG1 you've got your clock crystal choice, you've got your choice for your peripheral bus, and you also have a choice for your watchdog. And the watchdog is a special kind of circuit that's in the processor that allows the chip to reboot if something's going wrong. Okay, and what you do in order to make sure that that happens is you have the watchdog go at a particular frequency, and when it gets to a particular value, then you feed your watchdog. You give it you change a bit on it, and if it gets changed on time, it won't reboot the processor. If it doesn't get fed, if you don't give it the bit it wants, then it will say, oh, something's wrong, I didn't get fed on time, and it will then reboot the processor. Okay, so basically at this point you've got these different things that can be changed. You can select your oscillator. Excuse me. You've got your dividing bit, and you've got your primary oscillator configuration bits, all located in here inside of dev CFG1. Okay, so let's see. So all of that to also say that in order to get your chip working properly, it's important to get the clocking registers set up as early as possible, and that's going to be done through those pragma statements. So generally you need to do things like change the input divider. You need to be able to have a selection of what kind of oscillator you're dealing with. Okay, so that's all in here in these configuration registers. You say what kind of mode you want for your external clock. You say what sort of divisor you want for your peripheral. You say what kind of PLL multiplier you want, what kind of output divider you want for your PLL. So you've got your PLL configuration that you need to do, and your selection for your external clock, whether it's external or internal, okay? You also need to be able to say what you want for your peripheral as opposed to your regular system clock. These things need to be set in the initial stages of boot up for your processor. Okay, that's it for setup. Next, what we're going to do is we're going to talk about the actual timers. So once you've done all the setting up, then we can talk about the actual timing circuitry that's inside that actually gets work done.